Hi, we're Team 5, and this is renewable hydrogen production via electrolysis for fuel cell vehicles. The goal of our project is to propose a green and clean chemical process that will produce hydrogen gas via electrolysis from only renewable sources. From there, we will determine the feasibility of the hydrogen fuel cell against fossil fuels. The use of this alternative fuel will serve as a solution to tackle the United States greenhouse gas emissions and transportation as energy demands increase.
The general flow of our chemical process is to create electricity via renewable energy. Next, the electricity generated will be used in order to perform the water splitting required to liberate hydrogen from our water supply. This hydrogen will then be used in order to power PEM fuel cells. These fuel cells can be used for a variety of technological applications, but we have a focus on powering vehicles that travel on the land. Any hydrogen that isn't immediately consumed will be placed in storage tanks. Our first source of renewable energy is photovoltaic solar panels. The amount of energy entering the PV panel is primarily a function of incident radiation from the sun and the area of the solar panel. Solar panels are an overall detriment to the efficiency of the unit. A combination of heat removal systems and novel designing will be implemented in order to maximize the amount of electricity that can be generated from these solar panels. Our second source of renewable energy is offshore wind turbines, which will generate the majority of electricity for our electrolysis process. Generally, the amount of power generated by these wind turbines are functions of the area swept by the blades and the velocity of the wind. The size of these offshore wind turbines we'll be typically using have a power rating of about 4 to 12 megawatts.
The method we chose to produce hydrogen gas is a proton exchange membrane electrolysis, which is not very different from traditional electrolysis, only in that we place a membrane in the center of the electrolysis chamber to help drive the proton concentration to a specific region of the electrolysis chamber. Even though this method has slightly different reactions in the anode and the cathode, the overall reaction is still the same, where water is split into hydrogen gas and oxygen gas. Some of the benefits of this method is that it has a high efficiency with a value dwindling around 80%. It's also a reliable efficiency, meaning that this value does not oscillate very much. Some of the downsides of this method is that it's rather expensive, with the price being highly dependent on the type of membrane that is being used. With this method that we considered, we had to develop a relationship between electrical energy requirement and the temperature of the water when it's going into the electrolysis chamber. To develop this relationship, we consider some thermodynamic qualities such as the change in enthalpy, the change in entropy, and the change in Gibbs free energy. Considering these thermodynamic qualities led us to realize that we could create a relationship of electrical energy by taking into account the contribution of the environment into the system. We found out that there was interest in keeping the temperature of the water going into the electrolysis chamber high, such that we can produce more hydrogen gas with less electrical energy. And this also raised the question of how is it that we can raise the temperature of the water without imposing a new energy cost into the system.
In theory, PEM fuel cells utilize the reverse reaction of what happens in electrolysis. Here we have a dynamic model that shows what's happening inside of a PEM fuel cell. On the anode side of the fuel cell, we have hydrogen gas entering and being oxidized. When this hydrogen is oxidized in the presence of a catalyst, the electrons are taken from the hydrogen molecules and are used to generate DC electricity. The hydrogen protons are passed through the proton exchange membrane in the center. Any hydrogen that isn't immediately used is recycled to make another pass through the fuel cell. Simultaneously, oxygen is entered on the cathode side of the fuel cell. The hydrogen protons that go through the other side of the membrane are recombined with oxygen gas to create water vapor or liquid water depending on the design specifications of the fuel cell.
For our goals, the team intends to use a mixture of offshore wind turbines and solar panels for our energy needs. This causes a high initial capital cost. To lower the overall expenditure cost of our project, we look to minimize costs elsewhere. We optimized our solar panels using heat pipes to increase the feed temperature to lower the energy cost of our electrolyzer. By doing so at peak solar panel temperatures, we can lower the cost to produce hydrogen by 94.57% and have carbon-free hydrogen production.
This is a map of public hydrogen fueling stations in the country right now. As energy demand increases, there's an urgent need for renewable energy and alternative fuels. If our project becomes a reality, carbon emissions will decrease significantly. They will continue to decrease if more consumers switch to alternative fuels as well. With our optimized solar panels, our project can become a reality, and the map will look like this. Research on this topic is the only beginning. This could be our future. Thank you.